On July 22, 2023, a paper was posted claiming the creation of a room temperature ambient pressure superconductor LK-99. The world is now trying to synthesize the thing and replicate the paper's findings. The LK-99 Wikipedia page is keeping a running tally. The quest for a room temperature superconductor has gone on for over a century. It has seen some amazing highs and lows. In this video, let us dive into the dream and track the 100-year history of technological progression towards this mythical substance. But first, I want to remind you about the newsletter. Sign up for updates and new analysis, the full scripts of selected popular videos, and more. The sign-up link is in the video description below. I try to put one out every week, maybe two. Alright, back to the show. Resistance is a material's opposition to an electric current flowing through it. A conductor has low resistance, and so lets electrons easily move through them. Insulators do not. In previous videos, I have mentioned that all real-world materials have some amount of resistance. Of course, I was not thinking about superconductors, perhaps because I didn't consider them practical materials. We have known about superconductivity for over a century now. In 1911, the Dutch physicist and Nobel Prize winner Heike Kamerlingh-Onnes and his students started performing experiments at super low temperatures using liquid helium. At the time, people speculated on what might happen to the electrical resistance of metals as they approached absolute zero. Sir James Dewar, inventor of the vacuum flask, theorized that electrical resistance would infinitesimally approach zero. Lord Kelvin, on the other hand, thought that it would hit some minimum before quickly rising towards infinity, his reasoning being that the electrons would stop moving as it gets colder. So, Kamerlingh-Onnes did an experiment with mercury. Why mercury? Because it was the only metal they had available in sufficient purity. And unexpectedly, the experiment showed mercury's resistance falling to zero just below 4.2 Kelvin. Kamerlingh-Onnes named this state superconductivity. The temperature at which the material achieves this state is called the transition temperature. The first superconductors triggered a great deal of excitement. It was the electrical engineer's wet dream, a future free of electrical resistance. In 1913, Kamerlingh-Onnes traveled to Chicago and spoke of building a helium cooling plant in pursuit of smaller, more efficient motors or generators using superconductivity. Optimistic Kamerlingh-Onnes continued his work. He discovered that lead's transition temperature was 7.2 Kelvin, slightly higher than mercury. In 1914, he then made a coil of lead wire, froze it to 7.2 Kelvin, and passed an electrical current through it. But to his disappointment, the coil lost all of its superconducting powers when the magnetic field got to be about as strong as a horseshoe magnet. As it turns out, superconductivity requires not only a low enough temperature, but also a low enough magnetic field and a low enough amount of current passing through it, current density. The material can only maintain their superconductivity if all three sit within the parameters. Today, pure metal or simple alloy superconductors are known for this fundamental weakness. These are not good for practical industrial use. After all, electrical systems encounter magnetic fields all the time. Kamerlingh-Onnes must have been crushed. He was one of the first scientists to have fallen victim to the sirens of superconductivity. He would not be the last. Research on superconductor materials then slowed for a decade. The need for liquid helium cooling stood as a formidable financial barrier to continued commercialization, and there was no big market need pushing for it either. Many people worked on the concept simply because it fascinated them. Through them, pioneering science was done in the 1930s. We discovered three more superconductors: tantalum at 4.4 K, thorium at 1.4 K, and niobium, which has the highest transition temperature yet known at 9.2 Kelvin. In 1933, we discovered the Meissner effect. This is where a superconductor expels all magnetic fields as it transitions into a superconducting state. In other words, the magnetic field will go around the superconductor material rather than permeate through it. This explains why all the videos you see of these things are of them floating on magnets. And then a second major discovery that went under the radar. In the late 1920s, the Soviet-Ukrainian scientist Lev Shubnikov worked at a cryogenic lab in the Netherlands. In 1930, he returned to the Soviet Union and continued his research. There, his experiments discovered what are now called Type II superconductors. These are quite different from the pure metal superconductors today called Type I that so disappointed Camerleones. Type I superconductors fall back to normal behavior when they breach their magnetic limit. But Type II superconductors can display a mix of ordinary and superconducting properties at certain magnetic limits. So Type IIs can potentially be made to be far more tolerant of higher magnetic fields than Type Is. These are almost always complicated alloys or compounds. Sadly, Shrubnikov never got to see the benefits of his work. At the height of the Great Purge in 1937, the NKVD targeted him for his foreign connections. They arrested him, accused him of espionage, and shot him. It would be many years before the rest of the superconductor community recognized and capitalized on the significance of his work. World War II had shown the entire world the economic and military value of turning sciences into technologies. Shortly before the war, MIT professor Samuel Collins invented the Collins helium liquefier system. Widely introduced after the war, the Collins made liquid helium more available for superconductor research. Yet the search for higher temperature superconductors, perhaps even a room temperature one, remained quite difficult. We did not have good theory to tell us where to look, so most people started with metals with already low amounts of resistivity, copper, gold, silver, so on. In the early 1950s, a pair of scientists, B.T. Mathias and John Hulme, took a different approach. They embarked on a systematic search via experimentation. The two pioneered the method of finding superconductors via the Meissner effect, the superconductor's tendency to expel magnetic fields. They applied an external magnetic field to a sample as it was being cooled and measured whether it expelled that magnetic field. Mathias and Hulme systematically moved through the periodic table, eventually testing over 5,000 compounds. This was how they discovered the A3B superconductors, 3 niobium atoms and 1 atom of either silicon, tin, or aluminum. Yes, it's a terrible name. Anyway, these would hold the record for the highest transition temperature, 23 K, for 28 years. Mathias eventually formulated the Mathias rules for finding a superconductor, which, kind of like the pirate code, are more what you'd call guidelines than actual rules. Rule number 6 was, stay away from theorists. As you might expect, Mathias looked down on superconducting theory, calling them just descriptions. But the physics world wanted a theory to help guide their way forward, and in 1957, 3 scientists proposed a theory that did just that. John Robert Schrieffer, Leon Cooper, one of the namesakes of Sheldon Cooper, and John Bardeen. Recognize the name of that last guy? Bardeen won his first Nobel Prize in physics as one of the 3 inventors of the transistor. This theory won him his second. The theory was named BCS, named after its 3 inventors. BCS also stands for Bowl Championship Series. It was a system that helped select the matchups in top-tier American football college divisions. Cal hasn't won a football championship since before World War II, so I don't know why I cared to mention this. Let's move on. Anyway, BCS theory suggests that when a material enters a superconducting state, their electrons pair up. This is weird because normally they repel each other. But in that superconducting state, we have the influence of a new force called phonons. Phonons are measurable, energized vibrations in the material's crystal lattice. Thanks to attractive forces from these phonons, the electron pairs create a brand new form called Cooper pairs. Cooper pairs are exempt from the Pauli exclusion principle, which explains why 2 solid objects can't be in the same place at the same time, and also why all matter does not simply collapse into a single point despite everything being mostly empty space. I think I asked my mom that once when I was a kid. Thusly, Cooper pairs allow these electrons to act differently than they usually do, traveling through the crystal lattice without resistance. This part of the theory has generally held up over the years. Cooper pairs are key to superconductivity. The energy bond holding these Cooper pairs are quite weak, so they can be easily shaken apart by thermal energy. Thus, BCS theory does a good job of explaining superconductivity at low temperatures. Superconducting materials whose behavior is explainable by BCS theory are known as conventional superconductors. By 1960, we knew about 35 elements and 1,000 different alloys to have shown superconductivity under certain conditions. In 1961, scientists discovered a series of niobium-based alloys that retained their superconductivity in the presence of a stronger magnetic field. These were called high-field superconductors, and they theoretically allowed us to make large superconducting wires that perform far better than traditional copper ones. Such wires can produce very powerful magnetic fields using very little power. High-field superconductors achieved the original dream of Kamerlingh Onnes many decades ago, but even so, it took the industry until early 1970 to reliably and viably produce superconducting wire. Such superconducting wires eventually became the widely accepted method for producing MRIs. MRIs with superconducting wire remain the single biggest and most important commercial use for superconductor materials. In 1986, two researchers at an IBM lab in Zurich, Switzerland, were collaborating on a study on superconductors. Alex Muller was a senior research fellow at IBM who received the job basically as a stopover before retirement. He had gotten interested in the field after spending 20 months in New York. There, he observed IBM's massive Josephson computer technology project. That was a $300 million effort to build an ultra-fast computer based on superconducting digital logic switches. It ultimately failed. I will talk about Josephson and his learnings in a future video about superconducting circuits and their computers. Upon returning to Zurich in 1983, Muller recruited a colleague, Georg Bednorz, to look for superconductors in oxides. After a couple frustrating years searching around, they came across an article from a team of French scientists describing metal-like electrical conductivity at a rather high temperature, like 900 degrees Celsius high. That was interesting. Ceramics are traditionally known to be electrical insulators. After further experiments, the duo produced a ceramic compound of barium, lanthanum, copper, and oxygen that achieved superconductivity at 35 Kelvin, a legit breakthrough. As is so often in the land of superconductors, this discovery came as a total surprise. Bednorz and Muller first kept their results away from even their colleagues and their employer. They decided to first publish their results at a small but reputable German physics journal, apparently because they personally knew its editor. In April 1986, they submitted the paper, which was deliberately given a very disarming title: Possible High TC Superconductivity in the BALACUO system. They chose this title because the two were not sure about their result. For instance, the Meissner effect had not yet been measured in it. After some time, the paper was finally published in September 1986, but rumors had been circulating since July, and they shook the scientific community like an earthquake. Not only because ceramics, like I said before, were not seen to be good conductors, but also Bednorz and Muller were seen as outsiders to the superconductor community, working in a backwater of the IBM research machine. One prominent member of the community, jaded by false claims over the years, was tempted to simply throw the paper away when he first saw it. These new ceramics also violated the previously established rules of superconductors. It did not follow the Matthias rules, and not only that, it highlighted a hole in BCS theory. By then, physicists had largely adopted BCS as a reasonably rigorous explanation of superconductivity. And because BCS only worked in low temperatures, superconductivity in general was regarded as an exclusively low-temperature phenomenon. This discovery heralded a new class of ceramic oxide superconductors with high transition temperatures, higher than ever before seen, referred to as high-temperature superconductors, or high-T. Research teams around the world raced to replicate the results. In late November 1986, some 2 months after publication, the Asahi Shimbun newspaper reported that a team led by Shoji Tanaka of the University of Tokyo had successfully repeated the experiment confirming the results. A few weeks after that, Paul Chu of the University of Houston replicated the results. Chu's results made the headlines. More impressively, he believed that there were other materials out there with even higher transition temperatures. A race for new superconductors soon emerged, with the big line being 77 Kelvin, the temperature of liquid nitrogen. Various groups in Beijing, Tokyo, and the US traded papers back and forth. Then, in January 1987, Dr. Chu discovered a superconductor with a transition temperature above 90 Kelvin, breaking the so-called liquid nitrogen barrier. Chu held off publishing for as long as possible as he first tried to patent the material. Finally, in February 1987, he announced his marvelous technical breakthrough. This class of high-temperature superconductors is sometimes called 1-2-3 superconductors because they have 1 atom of yttrium, 2 atoms of barium, and 3 atoms of copper. There is also some oxygen attached, but whatever, it messes with the cool naming. These things are also more generally referred to as YBCO superconductors, cuprate superconductors, or rare earth cuprate superconductors. Oh hey, more rare earth stuff. Wonder who's the world leader in those. Anyway, all cuprate superconductors share the same structure. They are big layered compounds, kind of like cakes, layers of copper-oxygen separated from one another by insulating oxide layers. The superconductivity happens within those thin copper-oxygen layers. We aren't exactly sure how it works. Cooper pairs are probably involved, but differently from how it is in BCS theory, making them unconventional superconductors. Cuprates broke the nitrogen barrier, which meant that we can use liquid nitrogen to cool them rather than liquid helium, which is what we used before. This has significant cost benefits. Liquid nitrogen costs about 50 cents per gallon, while liquid helium, $24 per gallon. On March 15th, the American Physical Society held a special symposium on high-temperature superconductors specifically to talk about the results. Several thousand physicists gathered at the Hilton at what they now call the Woodstock of physics. The highlight was a special evening session dedicated to the discovery, held on Wednesday night in the Hilton Grand Ballroom. It was filled to the brink. The session started out at 7 p.m. and ended at around 3 a.m., a magical 8 hours long. A gold rush was on for new materials based on this breakthrough. Superconductor-related headlines hit the media like the New York Times. Business Week cried out, "Superconductors, more important than the light bulb and the transistor." The fever swept over Japan. Multiple ministries rapidly directed R&D spending into this new category. By 1988, MIDI's single biggest R&D expenditure was on high-temperature superconductors. The U.S., too, the White House even held a presidential conference on superconductivity in July 1987. Reagan proposed an 11-point plan to build new industries around this new technology. Tens of millions of dollars of federal R&D were funneled into superconductors. On the corporate front, IBM and Bell Labs faced off with one another. They joined the fray alongside a bunch of new startups with buzzy names like American Superconductor Corporation, Conductus, Illinois Superconductor Incorporated, and Superconducting Technologies Incorporated. The discoveries kept coming throughout 1987. By playing around with the original barium, lanthanum, copper, and oxygen ceramic formula, researchers were able to find cuprate superconductors with increasingly higher transition temperatures. But the gaps between science and technology can be quite large and take a long time to overcome. As it turns out, transition temperature was only one of the factors that engineers have to consider when building commercially viable systems. For instance, take superconducting wires for MRI machines. The original promise of high-temperature superconductors was that we can swap out more expensive liquid helium cooling systems for cheaper liquid nitrogen ones. Should be easy, right? But as Kamerlingh Onnes found out long before, superconducting wires need to also be able to carry high current densities and withstand very high magnetic fields. In other words, they need to meet their critical parameters. The cuprate high-temperature superconductors do indeed have much higher transition temperatures, but their other critical parameters are not as dramatically higher. There was also a substantial materials engineering problem. Cuprate superconductors are ceramics. complicated materials that are very brittle to work with. This by itself limited their usefulness as a material. They also work differently. If you recall, the cuprates are layered cakes, and all the superconducting happens within those single flat layers of copper and oxygen. This imposes big challenges on how we might achieve this superconductivity. If we want to produce a wire using this material, it needs to be done in a specific way in order to maintain good alignment over potentially hundreds of meters. So it took a substantial amount of time to eventually engineer wire using high-temperature superconductors. They do exist and are used for things like cables for power usage, but that took years to develop. And there are certain applications where the high-T cuprate superconductors still fall short of established technologies. Niobium titanium, established all the way back in 1970, continues to dominate superconducting wires for MRI machines, mostly due to their superior mechanical properties. The slow speed of commercialization dampened enthusiasm, and unfortunately high-temperature superconductors could not uncover that golden killer app that would stimulate more investment into the space. Over time, the hype receded as it became clear that the cuprates did not present a way towards room temperature superconductivity. The scientific community did not forget Bednorz and Muller, though. Just 16 months after their discovery, the two won the Nobel Prize in Physics, the record for the fastest recognition in Nobel physics history. Superconductor research continued for another high-temperature alternative to the cuprate superconductors. In 2001, a Japanese team discovered an interesting non-cuprate superconductor, magnesium diboride. Its transition temperature was 39 Kelvin, far below the cuprates, but at least much higher than the traditional low-temperature superconductors. Unfortunately, its behavior was conventional BCS, so a dead end. The next significant high-temperature discovery came in February 2008 when Dr. Hideo Hosono reported a fluorine-doped iron-based superconductor with a transition temperature of 26 Kelvin. This opened up a new branch of high-temperature superconductors separate from the cuprates. At the outset, there was a lot of hope. A few months, another iron superconductor was found with a transition temperature of 56 Kelvin. But progress there has since stalled. And then, recently in 2015, a team in Germany published a paper claiming superconductivity in sulfur hydrides at over 200 Kelvin and high pressure. Interesting, but again, nothing that has real-world industrial implications. And there have been some questions about superconductivity in these sulfide hydrides. One recent controversial room temperature claim was recently retracted by Nature magazine. The search continues for a room temperature superconductor, or even a relatively high temperature superconductor with fewer engineering compromises than what we already have. Is LK-99 really it? I don't know, but will it really change everything if it was? Is it really the next transistor? It is hard for me to believe that. When we dream of room temperature superconductors, we talk about things like levitating trains, compact MRIs, economical fusion energy, and the like. Well, they have been citing these things since 1986. Many applications are already technically possible with existing low-temperature superconductors, but there are real economic reasons why we don't have those today. For instance, magnets for maglev trains. The magnets are not a significant portion of the financial cost for these machines. It is tied to the cost of the land, the labor, the extensive planning, and the construction. And then there is always the chance that a room temperature superconductor, whether LK-99 is it or not, cannot compete with existing economic solutions. Look again at the MRI. Intuitively, you might think that this new generation of high-temperature cuprates would sweep out the old superconducting wire tech used for those MRIs like yesterday's trash. But it turned out to be far more subtle than that. Even today, 30 years later, 80 to 90% of today's MRI machines are still made with good old niobium titanium. Just working these things into wires might take years. Remember, these things are layered cakes. Imagine making a cake hundreds of miles long. Real-world applications might be years and millions of dollars away. But hey, I hope I'm wrong. I love the excitement around LK-99, no matter the outcome. The fascinating science of superconductivity is having another one of its unique moments. This only happens ever so often in the world. Let's enjoy it. Alright, everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.